Okay, we got this coffee maker problem. Get that Keurig going, get some French vanilla creamer up in there, get that tasting real good. All right, part A, C prime, that's just your derivative at 3.5. So go in between 3 and 4. Write those 2 points down, basic slope formula, right? Now, these next 4 problems, 3 through 6, are all no calculator. Remember, since the 2012 on, there's 4 problems without the calculator there. Just do your basic slope formula, and you know that's going to change it from ounces to ounces per minute right there. So part A is good. Now, part B, let's spend some time with that because that is with a theorem, and we got to practice those, okay? So is there a time at which that thing is equal to 2? Justify your answer. Now, if something must be true, you start seeing notation and, there's theorem talk right there. Remember that theorem video, you can rewatch that if you need to, but if you see the y value is equal to something, intermediate value theorem. If you see the derivative is equal to a number, which we do here, that's mean value theorem. And if you see derivative is equal to 0, that's when you're thinking Rolle's theorem. So at the very least, you could just see a derivative is equal to a number, and you could write down MVT, and you could hope to get some credit for that, all right? But that just says if you have any continuous and differentiable function, that the derivative is equal to that average rate of change from f of b minus f of a over b minus a. Now, this tells us it's a differentiable function. Differentiable means it's automatically continuous. So I just wrote down, for that theorem to apply, it has to be continuous and differentiable. So I wrote that down as continuous and differentiable. And then notice what I did. I did my f of b minus f of a over b minus a formula. So I did c of 4 minus c of 2 over 4 minus 2. Got those y values from the chart. Got 2 for that. And then so if my average rate of change is equal to 2, that means that derivative must also be equal to 2. So that's continuous and differentiable, and there has to be a spot where that derivative is equal to 2. The mean value theorem guarantees it. So yes, there has to be there. So watch that theorem video again if you need to. Letter C, midpoint Riemann sum. I'm pretty sure BC has seen this already. Might be the first time AB is showing it to you. I'm going to show this to you from scratch though. But when I see this, the first thing that jumps into my head, that's my average value formula. That's my 1 over b minus a times the integral from a to b formula. So that's what we're about to find here is the average amount of coffee in ounces of the coffee in that cup right there in between 0 and 6 hours or 6 minutes, sorry. Now, so that's my average value formula, but we're going to approximate the integral. When you see Riemann sum, that means you're talking rectangles, right, left, or midpoint Riemann sum, or if you teach trapezoidal sum, you're going to do rectangles in there. You don't need the picture. I got the picture. I'll show you the picture from scratch just in case that helps anybody, but you don't need to do the picture here. So there's the integral we need to approximate. The 1/6 carries down. Now it tells us you're going in between. This is typically what I do, and I use the numbers from the chart there, okay? So I'll actually show that with you from scratch. You're supposed to go from 0 to 6, and it tells us 3 equal subintervals. So that means you're gonna go 0 to 2, 2 to 4, 4 to 6. Those are the bottoms of your rectangle. So the bottoms of your rectangles are each going to have a base of 2. That's why when I did the area of the rectangles, I got 2 times something, 2 times something, 2 times something, because that's the bottom of each one of those rectangles. Now, what the right, left, and midpoint Riemann sum tells you, it tells you where to go to obtain your heights of those rectangles. So for example, if it says a right Riemann sum, I would start at the 6. That's why I would go up to the curve and draw the height, and I would use that first height as 14.5. If it said a left Riemann sum, well, I guess that would have been at 0 when it had a rectangle. But when it says a midpoint Riemann sum, it tells you to go in the middle between that first subinterval, second subinterval, and that third subinterval. I'm just going to go in the middle of those intervals right there, okay? So I'm going to choose 1. That's the height that I'm using. So I know the bottom of that rectangle is going to be 2. And then I got to use the height at that x equals 1. That's going to be the 5.3. And I'll show you with the picture in a second. And then I know this rectangle, the bottom is also going to be 2. And then I'm going to go smack dab in the middle between 2 and 4. I'm going to choose the y value when x equals 3. So when x equals 3, that y value is 11.2. And then the last one, again, that bottom part is going to be a 2. But you got to go smack dab in the middle between 4 and 6 and use the 5. Use the y value at x equals 5, which is 13.8. Now, sometimes those values will be negative, and you include the negatives with it, unless you're doing like a total distance traveled, which has absolute value bars in there. If you have absolute value bars in there, well, then even if they were negatives, you would make them all positives right there. But see, that's how I obtained those numbers right there. So I have videos you should have watched where I explain how to do the midpoint Riemann sum and the left and right, all without the actual graph right there. Now, if you wanted to, you can make the rectangles. I got the rectangles down here, where if you're going in between 0 and 6, what did I do? I said, okay, that's 0 to 2, 2 to 4, 4 to 6. And then I said, okay, instead of going up at 6 or up at whatever, you got to go up at the 1. That's where you would hit your curve, and then you draw the height over. Then you'd go up at the 3, hit your curve, and then in the middle between 4 and 6 is the 5. So that's where you would go up to the curve, and that's where you would draw the height over. And that's how it's making sense with the rectangles right there. And then it's just base times height, base times height, base times height. But without the calculator, I factor out a 2, and then just spend a little time doing your arithmetic carefully. If you need to go to the side and do the old school arithmetic and just write it down, carry the 1 over and stuff like that, go ahead and do so. But that was 30.3, so a third of that, 10.1 ounces. And we said with that 1/6 in front, that's the average amount of coffee in that cup between the 0 and 6 minutes. The average amount is 10.1 ounces there. Whenever you do the average value formula, those units will always agree with whatever it is that you're integrating. So the units for C of T is ounces, your average value is going to be ounces, okay? Because you're just averaging out how many, like when you average out your percent score, it's just a percent. It doesn't turn into like percent per minute or anything like that. All right, letter D I thought was probably the easiest part of this, but you got to be careful without the calculator. It just gives us a function, and then it says find the rate at which the amount of coffee is changing. And when I saw that phrase, I'm like, boom, that's just a derivative right there. So take a derivative. Remember, you carry down the negative 16. The derivative of that is 0. The derivative that carried down the negative 16. When you go e to the power, you're going to go e to that power times the derivative of that power. And then 16 times 4 is 64, but there's a decimal spot, so you got to move the decimal over. Negative times negative is a positive, and then you got to take the 5 and plug that in. So 0.4 times 5, that's going to give us 2. That's like 40 cents times 5. That's going to be $2 right there. And then you're going to just, I think they'll probably accept it with the negative exponent in there, but we can get rid of negative exponent. But you just did a derivative, and then that's in ounces. So when you do the derivative, that's going to turn it into ounces per minute. So that's a pretty easy letter D right there. When I first read it, I thought it was going to be something more complicated, but I was like, bam, I just saw the rate at which it's changing. That's just going to be the derivative right there. Lunar eclipse.